So horizontal and vertical translation, these are the two we're going to hit today. Now, if you do have questions, ask. Because I've seen it time and time again, and I can definitely tell, I can probably teacher sense that I can tell when y'all are having a question and don't want to ask it. And I don't want to try to pry it out of you, but if you do, if something doesn't make sense, ask, okay? And it's not going to be so much, and I find with vertical translation, we feel good with. Now, in the general form, and I stick with these pretty much when we do these here, for vertical translation is f of x plus k. Now, we use f of x just as the standard f of x function. It doesn't have to be f of x. If we're applying a vertical translation to say g of x, it'd be, g of x plus k. Or if we're applying it to m of x, it'd be m of x plus k, where k is the amount that we're moving the function up or down. If we move it up, the value of k is going to be positive. If we move it down, the value of k is going to be negative. Horizontal translation, we're moving the function to the left or to the right. Now, the standard way we write this is f of x minus h, where h is the value that we move the function to the left or to the right. Okay? Now, again, when we talked about this yesterday, or this yesterday and the day before, we said when we're looking at the function, left and right's the opposite of what we think. Because if we see it inside the parentheses or absolute value, we have x minus 4. It looks like it should go to the left, but it's actually going to the right, because the value of h, now I'll write it down just so we can see it, x minus 4 squared. H is our movement left or right. Now we can say h is indeed 4. Would the h value be positive or negative? It's going to be positive because it's x minus h. The x and the minus are from the formula. The actual value of h is 4, so it's moving right 4. If we had absolute value of x plus 3, h would be 3, but it would not be positive. It would be what? Negative. Because we're going left 3. Are we seeing this here? Because it's still, again, the fact that it's the opposite of what we think is still true. But when we talk about left and right movement, it's specifically the value of h. That value of h is still going to be positive, negative, depending on the direction. But as we see it and look at it after it's been applied, we do still have that opposite of what it looks. Does that make sense? Now, for the most part, with linear equations, equations of a line, most of these parentheses are going to end up going away at the end because we're going to resolve it out. We're just not going to leave a set of parentheses just hanging out there if they don't have to be there. We leave them with quadratics because it doesn't make it any simpler, any easier. Questions on this here? Vertical affects the output, our y values. Horizontal affects the input, the x values. So we look at this first one here. Let f of x equal 2x plus 1. Write a function g whose translation is 3 units down. So I'm going to write it out in the general form. G of x equals f of x plus k. We use f of x because that's the starting function, the one we're applying this to. And k is the amount that we move it up or down. Now for us here, what's our value of k going to be? Well, k is what? 3 units down, so k would be negative 3. Yes? Do we normally write plus negative 3? No, we just say what? We normally just say minus 3, yes? So we're moving it down 3. We are subtracting 3 from our y values. Questions on what we've done so far? Now we do need to replace f of x with its function. Because f of x, we're going to plug x into f of x. Well, and that means in every x, and 2x plus 1, we're going to replace with x. I'm replacing x with x. Because we have 2 times x, well, it's just going to be 2x plus 1. Because f of x, we're just plugging x back in, we really just get the function back. We didn't really do anything to f of x, so it's still going to be our 2x plus 1 minus 3. Now with quadratics in these transformations, we'll leave the parentheses alone because we'd have to do a few more steps. We'd have to actually multiply it out. But here, is there a number in front of the parentheses that we need to distribute, or a sign that we need to distribute through? No. Is there an exponent attached to these parentheses? So what can we do with these parentheses? We can just drop them. We don't need them. So it tells us that we have the function 2x plus 1 minus 3. Now, as long as we don't have any like terms, we're done. Do we have any like terms? We do. What are they? 1 and 3, we have 1 minus 3. 1 minus 3 is? So our new function g of x is 2x minus 2. And that's it. Up and down is nice. Left and right. Again, before we get there, we feel good about up and down. Yes? Now, I'm going to rewrite f of x. You do not have to rewrite f of x. Okay? I almost feel like I need to give a motion sickness warning for the people watching, but the reason I'm rewriting f of x is for this problem here. I don't want to be doing this for this entire part. Does that make sense? Because I can't, just from the screen, the f of x function is not listed. It's listed above, so I don't want to scroll back and forth. But y'all's note sheet, you can still see it right there. Okay? So for some of this here, some of this section, I'm going to be rewriting the function, so I'm not scrolling up and down. Make it a little bit nicer so we're looking at the same screen the whole time. Now, here, it says we want to write a function h of x, whose graph is a translation 2 units to the left of the graph of x. Now, in the general form, so we're applying it to f, so we'll use f of x minus h. This is the general form for it. Where h is the movement left or right. So how far are we moving it to the left or right? 2, yes? Because it says write a function h whose graph is a translation 2 units to the left, yes? So h is indeed 2. Now, would the value of h be positive or negative? It is left. So h specifically is going to be negative. Now, it will, because again, we're used to x plus 2, because again, opposite what we think. But specifically, the value of h is still negative because we are going to the left. Yes? Now let's see what happens. Because when I plug that value for h in, I plug that negative 2 in for h, I get x minus negative 2, yes? Do we normally leave something as minus and negative? Well, no, we just say it's what? Negative and negative make a plus. That's where we get that plus, that opposite. Because of the negative from the form, the general form causes that sign to flip. Because when h is positive, we're moving them to the right. H is positive 2. We're moving right. But when we plug it into the general form, we get x minus 2. And here we're moving left. Our value of h is negative 2, but when we plug it in for its spot for h, it changed it from looking like negative 2 to now it looks like positive 2. We still see that? Okay. Questions on this so far? So now the function we're looking at is what? F of x plus 2, yes? Well, what function did we start out with? F of x, yes? So what did we change? We changed what? We changed this x to x plus 2, yes? I've replaced the x in the normal function, the function we had to begin with an x plus 2, yes? So what are we going to do to this x here? We're going to put x plus 2 in place of it. So we start finding our new function. We have to replace that x with x plus 2 because we're not looking at the function f of x anymore. We're looking at the function of x plus 2. Now our 2 on this side of the function is still going to be there. We don't have x anymore. We have x plus 2 plus 1. Questions on this here? Any question on anything we've done so far? Okay. Because I feel like people are getting this part, yes? Because this here is the trickiest part of, I feel like, of what we're doing today is just understanding how we're plugging that in. Now, at this point here, we just need to simplify. We have the 2 in front of the parentheses, yes? So we have to distribute through. 2 times x is 2x. 2 times positive 2 is positive 4 plus 1. Do we have any like terms? 4 and 1, yes? 4 plus 1 is? So h of x is 2x plus pull the graphing calculator up. So I put the first 2 in already. I put them in 4th hour. So 2x plus 1, 2x minus 2. So 2x plus 1 is the one in blue. We said the first one we moved it down 3. Yes, we can see graphically it's moving down 3, yes? Now the question is, well, our new one, 2x plus 5, needed to move all of these points 1 unit to the what? Or 2 units to the left, yes? It did indeed move everything 2 units to the left, yes? And what that means, if we looked at this, y equals, I'm going to clear the 1 out in the middle. Here, 2 units to the left. So at the original point, 0, 1, yes? If I move it 2 points to the left, so now at negative 2, I should have 1. The y value, essentially we moved everything over 2. So its corresponding x should be 2 less. 0, 1, move it over negative 2, 1. Where we have 1, 3. 1, 3 is our point here for the original one. If I move it over 2, it should now be a negative 1, 3, which we can see that it is. Makes sense? Kind of, I mean, not hugely involved, but this here is our function. Questions on this here? We're going to look at more. We're not done just chewing out. Let's look at the next one. F of x equals 4x minus 9. Write a function g whose graph is a translation 5 units up of the graph of f. So g of x would equal f of x plus k. Well, what would our value of k be here? 5. Would it be positive or negative? Positive. So we would say plus 5 because we're moving it up 5. Now, because we didn't do anything to f of x, it's still just f of x, we can just replace it with its function. Now, we don't necessarily need the parentheses because there's nothing in front of f of x, there's nothing we're doing to it, so we can just drop those. Telling us that we have 4x minus 9 plus 5. Negative 9 plus 5 is? Questions on this here? We feel good with this here, up and down. Up and down we normally feel good with. Now, you don't have to erase anything. I just want to mess with this number a bit. What if I said I wanted to move it up 9 instead? Well, I would replace k with 9. We'd get 4x minus 9 plus 9. 4x minus 9 plus 9 would be what? 0. So we would just have 4x. There's nothing saying that we can't just lose a term because we moved it up. That 9 is now gone. Yes? It's just 4x. That is possible. In fact, I never wrote the 5 back in. All right. We're ready for the left-right. A function h of x, whose graph is a translation 1 unit to the right of f of x. So what would our value of h be for this one here? 1. Would it be positive 1 or negative 1? It'd be positive because we're moving to the right. So when we plug it in, substitute the value of h in, we get f of x minus 1. F of x minus 1. Because again, we still have that opposite thing going on. H is still positive or negative based off the direction. We only get that opposite, that flip, when we put it back in. Yes? Okay. How would we write this next part? Yes, we'd plug x minus 1 back in for x, giving us 4. Parentheses minus 9. So we feel comfortable with that, yes? Okay. I just want to make sure, because the number of years I keep getting yes for some classes, and it's really a no. Are we done? We got to distribute the 4, yes? 4 times x is 4x. 4 times negative 1 is negative 4. Negative 4 minus 9 is and that's it. Questions on this here? We ready for the next one? F of x equals 3x. We want to make it a translation of 5 units up. We'll call it g of x. It really doesn't matter. This would be our f of x plus k, or f of x plus k. Well, k is what? 5 up, yes? So we could say plus 5. F of x is 3x plus 5. Do we really need the parentheses? Two ways we can go about it. One, we just drop them. Giving us this here, yes? Or get the same answer. But again, it's good to use the parentheses just in case, like for especially our left-right, where we have that distributed part, we have something that has to happen to it. Because if we put them and don't need them, all we got to do is remove them. If we forget to put them and we need them, it's going to cause issues. I'd rather put too many parentheses than not enough. Let's look at the last one here. I'm just going to call it g of x. F of x minus h, where h is our movement left or right. Well, for us here, our value of h is 4. Would it be positive or negative? Positive. So when we plug that h in, we get x minus 4, f of x minus 4. Now at this point here, just like before, we have to replace every x in f of x with x minus 4, which does give us the absolute value of x minus 4 minus 3. Yes? Again, we don't need the parentheses inside the absolute value, so we drop them, giving us the absolute value of x minus 4 minus 3. Yes? Do we have any like terms? I mean, yes and no. I mean, 4 and 3 are like terms, but the 4 is trapped inside the absolute value. We can't just move it through. So this here is final answer. That's it. How do we feel on horizontal and vertical translations? Pretty good. And the biggest thing I would say with horizontal and vertical translations, any of these translations, sticking with these here, starting with these here and plugging in the translation into that form is going to make these nicer because it organizes it and helps us be able to apply it in a systematic way. The next one we have is reflection across the x-axis and across the y-axis. Reflection across the x-axis and across the y-axis. Now again, with reflections, we do have a setup. If it's a reflection across the x-axis, we have negative f of x. If it's across the y-axis, we have f of negative x. Negative f of x, f of because again, y-axis, if it was positive, the y value is now negative. If it was negative, it's now positive. We're changing the sign of the output. Across the y-axis, we're changing the sign of what we're putting it in. We're flipping it across the y-axis. So we change the input by that negative 1. So if we let f of x equal the absolute value of x plus 3 plus 1, we want to write a function g whose reflection is a reflection in the x-axis. So we're reflecting it across the x-axis. So according to our form, our general form for reflection across the x-axis, it's negative f of x. So to show this translation, we would say that g of x is equal to negative f of x. So just like before with our up-down, we didn't change f of x. F of x is still f of x, yes? So we still have the absolute value of x plus 3 plus 1. But this time it's a little different than up and down. We now have a negative out in front of that parenthesis, yes? Which means we have to distribute this negative through. Now, when I say this, when we say we are distributing it to each of these terms here, so we multiply by the absolute value, it's just going to be negative absolute value of x plus 3. We cannot take that negative into the absolute values. Because we're saying that whatever that value is, it's going to be negative. That's coming out of it, yes? If I put that negative into the absolute values, it's going to turn it and come back out positive. The negative goes in front. We're not just going to throw stuff through absolute value bars. It's like trying to drive a car through a brick wall. It ain't going to happen. I mean, it can. I would say I would prefer not to do that. Now our negative times our 1 is going to make it negative 1. And that there's our new g of x. Questions on this here? Now our next one here, we have h of x. Here's a reflection in the y-axis. Well, our y-axis is f of negative x. So this time, just like with left to right, we're now replacing every x in f of x with negative x. So we still have the absolute value bar, but instead of x, we have negative x. Don't need the parentheses, so we can drop those, giving us the absolute value of negative x plus 3 plus 1. That's it. I know we're going a little quick, but are we good? Okay, cool. And again, this is why I like these general forms, especially with these translations.
Ask the following students to the high school office, please. Sydney Swift, Lily Russell, Sophia Leroy, Chase Lundin, Madison Hancock, Jay Miller, and Butterfly. Thank you.
The reason I like these general forms is it does not matter the function. It does not matter what the function is. It doesn't matter what the function looks like or how it's set up. We can apply it to each function every single time. And it's going to work every single time. So f of x equals the absolute value of x minus 5 minus 4. Write a function h whose graph is a reflection in the x-axis of the graph. I'm hoping to be able to start fixing these slides soon, because this is additional problems from the teacher book. I do not have access to the teacher PDF at the moment. I will be getting access to it eventually so I can redo these slides. Because I don't think it looks too bad, too blurry from where y'all are sitting. Once we're done, I'm going to have you come up here and look at it a little closer. It's a little blurry. H of x. So since it's across the x-axis, we're going to say it is negative f of x. So we replace f of x with its function. We have absolute value, x minus 5 minus 4. And just like before, we're going to distribute the negative through, which will give us negative absolute value of x minus 5, and the negative 4 is going to become positive 4. Questions on this here? Are you ready for the next one? Let f of x equal the absolute value of x minus 5 minus 4. We want to do a reflection in the y-axis. So we'd say g of x is equal to f of negative x, yes? So this is going to equal the absolute value of negative x minus 5 minus 4. Out the parentheses, we have this here. Questions on anything we've done so far? How do we feel about reflections in the x-axis, y-axis, horizontal translations, up, down, left, right? We feel good about this here? So, because we said this one here, math absolute value of x minus 5, was it plus 4 for this last one? Minus 4. Make sure this is not. Yeah, minus 4. This was our starting value. And what we got was negative x minus 5 minus 4. And this was a reflection across the y-axis. We can see that it is. It did flip it across that y-axis. I want to try something. Well, I say try. I already know the outcome. What happened? It covered up the one in red, yes? Now the question is why? What is in common with these two here? They're both negative, yes? Now this is something that's not, we can't do with every type of function. It's specifically absolute values and quadratics. Because if we take the absolute value of a negative, it becomes positive, yes? And we can see both of those do have a negative. So if I factor that negative out of both terms, it's going to take it from negative x to positive x, and from negative 5 to positive 5, yes? Now, properties of absolute values. One of our properties states that if I have two things multiplied inside of an absolute value, it will have the same value as the product of each absolute value. So the product, the absolute value of m times n is the same as the absolute value of m times the absolute value of n. Okay? Now the reason I say that is because if we look at this here, that means I can say that this here is the same as the absolute value of negative 1 times the absolute value of x plus 5 minus 4. What's the absolute value of negative 1? 1. So we just have 1 times that absolute value. Which really just leaves me with the absolute value of x plus 5 minus 4. Can you now see why that overwrote the other one? They are the same, yes? If they're the same, is there any reason to do this? No. They have the same value. This is why they have the same value. There's no reason to rewrite it. is there are some problems, especially one of the ones on the homework, if you end up looking it up, you'll probably get that g of x or whatever it is equal to the absolute value of x, negative absolute value of x plus 3, whatever it is. If you ended up looking it up and checking it, it'll tell you, no, the correct answer is absolute value of x plus 3. What did we just say? I could pull that negative out of every term, get rid of it due to the properties of absolute value. They are the same equation. It is the same answer. I will take either one. I'll still take it as the negative. It's still the same answer. Does that make sense? Above and beyond. Okay? Some of the quirky things of mathematics. Do we need to see another example of reflections? Or do we feel good with reflections? Okay. We're going to stop on horizontal stretch and shrink and vertical stretch and shrink. Because horizontal stretch and shrink and vertical stretch and shrink, I'm going to point this out. So if you're kind of vertical stretch and shrink is nice. Vertical stretch and shrink is exactly like we see it. If we say that we have a vertical stretch of 4, we plug that vertical stretch amount in place of a. 4 times the function. If it's a vertical shrink of 1/2, we plug 1/2 in place of a. We feel good with that there. Yes? Horizontal stretch and shrink. Like I said, left and right, when we plug it in, it's the opposite of what we think. It's not, because h, if we're moving it to the right, h is 2. We plug it in, we're now plugging in x minus 2. Left, negative 2, it becomes x plus 2, yes? Let's see what horizontal stretch and shrink says. The graph, y equals f of a of x, is a horizontal stretch or shrink by a factor of what? 1 over a. So if they tell us it's a horizontal stretch of 2, I don't plug in 2 for a. I plug in 1 over 2. If it tells me it's a horizontal shrink of 2/3, we're not technically plugging in 2/3. We're plugging in 1 over 2/3. You see what I'm saying with horizontal stretch and shrink? Because I mentioned it yesterday, that's a little tricky. And it is and it isn't. It is because I can't take that amount and just plug it in like we've been doing everything so far. 1 over it, we have to flip it. Once we get that down, the fact that horizontal stretch and shrink, we have to flip it before we plug it in, then it's the same. That's the only thing we had to do for horizontal stretch and shrink is we have to flip that value. Because 1 over 2 is 1/2. I flip 2, it becomes 1 over 2. Which we get, we can kind of see that. 2, 1 over 2, 1/2 is the flip. Now if I said 1 over 2/3, if we flip 2/3, it becomes 3/2. We flip the top and bottom. 1 over 2/3 is indeed 3/2. That's why horizontal stretch and shrink can be tricky. Okay, so we'll stop there.